Hello, everybody. Welcome to the Mindscape podcast. I'm your host, Sean Carroll, and today we're going to go looking for life elsewhere in the universe. I think that with the discovery of many new planets around stars over the last few decades, the idea that there might be life elsewhere in the universe has become more and more of a scientific project. Of course, we've always been looking for it. We've been wondering. We've been doing the search for extraterrestrial intelligence and so forth. But now we have a more focused idea of where we might look and a little slightly more optimistic perspective on how many places there are out there where life could be. We also talked on this podcast previously about the idea of the origin of life. I mean, if life only ever existed on Earth, then the search for it elsewhere would not be very helpful. But we talked to people like Kate Adamala, to Sarah Mari Walker, about why life came to exist in the first place. Today we're going to roll up our sleeves a little bit and think about looking for life. And it's one thing to look for extraterrestrial intelligence very, very far away. Today we're going to talk about looking for actual living beings here in our solar system. People of a certain age, namely my age, came of age at a time when we were looking for life on the surface of Mars with the Viking landers in the 1970s. It was very exciting, but also a little bit inconclusive. We didn't find any life. Mars is a pretty dry planet, and these days we talk a lot about whether or not Mars might have had life in the past, less so about whether it has life now. But don't get the wrong idea, because there's other places here in the solar system where life really could exist, and we are actually going to go look for it. Today's guest is Kevin Hand, who is Deputy Chief Scientist for Solar System Exploration at the Jet Propulsion Laboratory here in Pasadena, California. Kevin is educated in physics and geology and biology and astronomy and planetary science and all of these things, mechanical engineering. He brings them together, both thinking about what life might be and how it might arise, and how we might actually build something to go look for it. His special focus has been on Europa, the moon of Jupiter, but he also thinks about Enceladus and Triton and Titan and other places in the solar system, typically moons of giant planets, where you can get oceans underneath giant sheets of ice, which might be just the right conditions for life to form. Kevin has a new book out called Alien Oceans, which is exactly about this topic, looking for life here in the solar system. Probably not technologically advanced life, don't get too excited, but it's very, very plausible that microscopic or primitive forms of life could exist elsewhere in our backyard. And it's very exciting to think that we're going to go look for them. I wanted to mention very briefly that, we have a Patreon here for the Mindscape podcast. You can find links to it on the podcast webpage or just at patreon.com/Sean M. Carroll. But we also do, for the Patreon supporters, they get ad-free versions of the podcast and also a monthly Ask Me Anything episode. And now we've let the Ask Me Anything episodes go public. This was a vote taken by the Patreon supporters. So only Patreon supporters can actually ask questions, but everyone can hear the answers. So I will put these on YouTube, and also the actual Patreon post where my answers, where the episode with my answers is put, becomes public a few days for everybody after I post it at the beginning of the month for the Patreon supporters. So check that out. Also check out the video series that I am doing called The Biggest Ideas in the Universe, where once a week I tackle a big idea, talk about it in hopefully a compelling, informal, chatty kind of way. And then a couple days later, I'll do a Q&A video about that. So a lot going on here at a time when many of us are locked down looking for things to do. We're trying to provide content for everybody so your minds don't atrophy. You got to be thinking. You got to be moving forward brain-wise in this time of quarantine. And with that, let's go. Kevin Hand, welcome to the Mindscape podcast.
Thank you, Sean. Good to see you.
Now, I've heard that you just got back from Antarctica, and did you find life in Antarctica?
Plenty of life.
Not that hard, really. You're not really giving yourself a challenge here.
That's right.
Why were you there?
So our team was testing out and deploying this under ice robotic vehicle that is something that JPL has invested in as sort of a win-win robotic capability that can be used to study Earth's ocean and Earth's cryosphere, Earth's ice. Well, simultaneously building some of the capabilities that someday we hope to deploy beneath the ice of a world like Jupiter's moon, Europa.
Okay, so you're there at a place where there was ice on top of water and sending it into the...
That's right. Sea ice around Antarctica.
Is this something where the thing you were dealing with had a capability of digging through the ice, or did you cheat by
No, we're not there yet.
Okay.
So someday we will have this robot encased in another robot, and that other robot will have the job of getting through the ice.
Are you going to put the whole thing on a rocket, send it to Europa?
Someday to Europa, but doing what I just described, getting through ice, even thin ice, the ice that we were dealing with in Antarctica down at the Australian Antarctic Division's Casey Station. They were great partners. That ice is just about 160 centimeters in thickness, at least when we were there.
That's nothing.
Nothing except to get through that ice and then deploy our robotic vehicle. Takes chainsaws and ice chippers and all sorts of things, and projects that work to get through even thicker ice on Earth use hot water drills and just thousands upon thousands of kilograms to get through the ice before you can even start to sample what's beneath the ice. And so, as you can imagine, if our dream of dreams is to someday get through the ice of Europa and directly study that ocean and whatever may be alive within it, we've got a long way to go. And so there's this beautiful win-win.
How thick is the ice, we think, on Europa, roughly?
Well, that's a huge debate. There are the thin shell ists and the thick shell ists. I happen to be on the thin shell
But
side.
you kind of got a plan for a thick shell if you're sending up the spacecraft.
So to be clear, by thin, I mean about, let's call it 5 kilometers in thickness.
Right.
So it's still pretty darn thick.
More than 180 centimeters.
Yeah, exactly. You're not going to chainsaw through that. So
Okay.
it's by Earth standards. So the Antarctic ice sheet above Lake Vostok, which is one of these subglacial lakes on the continent of Antarctica, the ice above Lake Vostok is about 4 kilometers in thickness.
Okay.
And that would be considered thin ice on Europa.
Right.
And we can't even really access these subglacial lakes in Antarctica easily. So
Even with all of our human capability of flying down there and having people
huge
and
tractors
chainsaws.
full of devices to hot water drill, et cetera.
So this is depressing me. This is making me think that it's less likely than I imagined to easily just dig down into Europa's oceans.
Welcome to my world.
Yeah, okay.
That's not for the faint of heart.
So we're just, the audience here, we don't presume they know anything at all. So we'll get to what Europa is and why it's interesting, but is there a mission planned to go do this, or is this just planning for future far off things?
There is a mission that NASA has committed to called the Europa Clipper mission, and that mission is a flyby mission. It will orbit Jupiter and fly by Europa some 45 or more times. And with each flyby, some of which may be fewer than 100 kilometers above Europa's surface, with each flyby, it will collect incredible imagery, spectroscopy. It's got an ice-penetrating radar instrument on it to essentially sound into the ice. And so it's got all sorts of great ways of looking at Europa's surface, looking into Europa's interior, figuring out the surface chemistry, the surface geology, and some of the interior geophysics. And that's from a remote sensing mission, a mission flying by.
Right.
That mission does not have any lander on it. I'm part of the Clipper mission, but much of what I focus on at JPL is the next step, trying to get a lander down to the surface of Europa, or for that matter, Enceladus, a moon of Saturn. That is also incredibly compelling in the context of alien oceans beyond Earth and places where we could go to not just find evidence of life, but find extant life that is alive today.
Right. Not just fossils.
Not just fossils. And that's incredibly important in terms of kind of revolutionizing our understanding of biology.
Do we know for sure that there are oceans beneath the ice on Europa's surface?
Well, you, of course, know that for sure needs to be in quotes, but based on the available evidence, we can make the prediction that the best hypothesis to explain the available evidence is that Europa does have a salty subsurface liquid water ocean. And that evidence I like to kind of partition into 3 easy pieces.
Okay.
Kind of taking a page out of Feynman's 6 easy pieces, right? And the first easy piece is use spectroscopy to figure out that the surface of Europa is covered in water ice.
Uh-huh.
And
Rather than methane
or rocks or whatever, right? Think about it. 1610, Galileo turns this military tool, the telescope, to the night sky, looks at the moon, looks at Venus, looks at Jupiter, and sees Jupiter and also sees these 4 little points of light, which to him at the time he thought were just stars.
Stars, what else could they be? Yeah.
Right, yeah. And Galileo, being a clever fellow, named them the stars of Medici because, of course, that's where his money was coming from.
You would name them the stars of NASA. That's where your money's coming from.
Right. So, but as we know, he mapped those little points of light around Jupiter night after night and discovered that they, in fact, revolve around Jupiter, which at the time was heretical and got him in trouble with the Spanish Inquisition. But through his diligent observations, we came to appreciate that Jupiter has moons. Now, those little points of light stayed as points of light for some 350 years until astronomers like Kuiper and Vasily Moreau, a Russian astronomer, used spectroscopy to figure out that the surface of Europa was made of water ice. So that's the first easy piece. Okay, we go from a point of light to Europa having an icy surface.
Right.
The next easy piece, I like to make the analogy to babysitting a spacecraft.
Okay.
What do I mean by
Something
that?
we've all done.
So babysitting a spacecraft. Well, here on Earth, we use the Deep Space Network, this network of antennas, 3 of which are 70-meter antennas, to get the data back from spacecraft and to send commands up to spacecraft. The DSN is used for all missions. And along with collecting and transmitting data from the various spacecraft, the signals that are received can be used to look at the tiny red and blue shifts, the Doppler shifts, associated with those signals.
Sure.
And phenomenally, this never ceases to amaze me. With the Galileo spacecraft, as it was flying by Europa, the beautiful little gravity well, and you know, you're the expert on all of that and the fabric of space and time, but Europa's got its own little gravity well, and as the spacecraft flies by, it causes Europa's interior mass distribution and its rotation cause slight accelerations and decelerations, which appear as millimeter per second Doppler shifts in the signal being sent back to Earth.
So Europa is not a point mass. We can't just...
That's right. And not only is it not a point mass, but by merit of looking at the gravity signal of Europa, in other words, the Doppler shift as the Galileo spacecraft flew by, scientists on the Galileo mission were able to tease out the moment of inertia of Europa.
But sorry, we're looking at the Doppler shift of the spacecraft.
Sending its transmission back to Earth.
Okay, but it's influenced by Europa, and because Europa is not a point mass, it has a shape.
That's right.
It's not a perfect sphere.
And
that's what you can look
and
at.
not uniform density.
Right.
And so the rotation plus the non-uniform density puts its fingerprint on the Doppler shift of the spacecraft as it flybys. And then you can invert those that information about the gravity structure of Europa to get things like the moment of inertia, from which you can then build layered models. Okay.
So you say such and such rock, such and such water, such and such ice.
Exactly. So the second piece of the puzzle is that the gravity data, those Doppler shifts, necessitate that Europa, at least in kind of a 3-layer model, has a dense core, iron or iron and sulfur, a rocky silicate mantle, and then some outer layer of roughly 100 to possibly 200 kilometers in thickness of low density material. And in particular, the density that fits the gravity data well is something in the range of 1 gram per cubic centimeter.
Also the density of the glasses of water in front of us right
exactly,
now. Yes.
Right. And so the second piece of the puzzle follows on the first. The first says you know that Europa is covered in ice. The second piece of the puzzle tells you that water in some phase, be it liquid or solid, extends down for 100 to 200 kilometers. Now, the gravity data was not of sufficient sensitivity to differentiate between the density of water and the density of ice.
Sure. It's a miracle they could do anything at all. Astronomers are just geniuses at taking the tiniest bit of data and stringing a tale based on this.
Oh, it's remarkable.
It's remarkable. Yeah.
But I always feel compelled to point out, we scientists often have the easy part of the job. It's the engineers who really make this possible. They make the data possible.
Yeah.
Without their precision, you don't get that millimeter per second velocity difference that you're able to measure. So that's the second piece of the puzzle. We're not yet at an ocean. That requires the third piece of the puzzle. A liquid water ocean, a salty
right, because
liquid water ocean.
Given the first two pieces, it could just be all ice.
That's right, exactly. And so the third piece of the puzzle, I like to make the analogy to adhering to airport security.
Okay.
What the heck do I mean by that?
What do you mean?
So for the moment, disregard those big cylinders that we sometimes now have to walk in and, we feel like
Yeah.
we're being zapped in 1,000 ways. Go back to those doorways, the traditional metal detectors. Mm-hmm. When you're at an airport and you're walking through one of those doorway structures, you're passing through a pulsating, time-varying magnetic field. That time-varying magnetic field gives rise to electric currents in any conductor that you might have in your pocket or on your person. Those induced electric currents, as we know from Faraday and E&M, those induced electric currents give rise to induced magnetic fields. Mm-hmm. And within the little doorway, there are sensors to detect induced magnetic fields. So you walk through with a conductor in your pocket, that gives rise to induced electric currents, which gives rise to induced magnetic fields, and the alarm goes off.
Yeah, we've all been there.
All been there. Then you get the pat down, you miss your flight, et cetera. Right. So with the Galileo spacecraft, the alarm went off. The Galileo spacecraft had on board a magnetometer, a fancy compass. And as it flew by Europa, it detected an induced magnetic field. It had long been measuring, the Galileo spacecraft, had long been measuring Jupiter's magnetic field. And from that data, we knew that Jupiter's magnetic field is tilted by nearly 10 degrees.
From Jupiter's rotational axis.
Exactly. And so if you're Europa, Jupiter's magnetic field has a time-varying component. Mm-hmm. So the Galileo spacecraft had mapped that out reasonably well. And as it flew by Europa on a handful of occasions, it detected an induced magnetic field. What the heck could be giving rise to an induced magnetic field? Europa did not have a standard dipole the way the Earth does. It did not have an intrinsic field. It had this induced field. Well, you could say maybe the time-varying component of Jupiter's magnetic field is interacting with Europa's iron core. Iron's a good conductor.
Yep, that makes sense. That would be my answer, yes.
Sets off the alarm. Well, you do the math and the modeling, and I did a lot of this a number of years ago and tried to fit things. The core is just too small and too far away. What about that rocky mantle? Turns out that rocks, silicate rocks, are not conductive enough to explain the data. But what fits the induced magnetic field data of Europa beautifully is a near-surface conducting layer. Now, from piece number 1 and piece number 2, we know that that near-surface region of Europa is water in some phase.
Right.
And so the best answer to the induced magnetic field data at Europa is a salty liquid water ocean. The salt provides the conductivity that explains
Water by itself would not work, but
water
salty
by
water
itself,
would work.
Exactly. Yeah. And so
And liquid water is better than ice.
that's right. Yeah. You can kind of play around with some mushy ice scenarios, but even in that, you're essentially at an ocean anyway.
I mean, it's both remarkable that we can say all that about a little dot in the sky that Galileo looked in his telescope. It's also very vivid that we could be wrong, right? I mean, like you said, we never know for sure. There's a lot of great evidence, but presumably the Clipper will give us much more evidence.
That's right.
What year is that coming?
Well, so hopefully the mission will get to the launch pad in the 2023 to 2025 timeframe.
Okay.
Either launch would hopefully get us out to JOI, Jupiter Orbit Insertion, and ultimately flybys of Europa in the late 2020s.
Okay.
And a lot of that uncertainty is in what launch vehicle we actually go on.
But it could be roughly 5 years to get there.
Yeah. On the low end, closer to 3.5, 4. On the higher end, closer to 6.5, 7.
Yep. Okay. Let me pause for a moment to talk about policygenius.com. Those of you who know about my interest in the arrow of time understand that the past is something we can understand from memories and records, whereas the future is up for grabs. We can do things today that lead to good outcomes or bad outcomes. And furthermore, things can happen to us that we would consider to be good or bad. We can't control the future perfectly, but what we can do is hedge our bets. And that's where insurance comes in, whether it's life insurance, home insurance, auto insurance, and so forth. When the worst happens, you have a policy there that will help you out. The trick is choosing the right policy, and that's where Policy Genius comes in. Policy Genius is a way to look at many different offers from different life insurance companies. Choose the one that is best for you. The Policy Genius team can handle all the paperwork and all the red tape. It takes the worry out of choosing the best life insurance for you. So even if you think you've made mistakes that have led to bad things, you'll never be distressed about life insurance with Policy Genius. In just a few minutes, you can find your best price and apply at policygenius.com. And then the lander, if let's say that everything works and you get the lander, you get the money, you get the launch date, when would that be arriving at Jupiter? This is your baby, right? This is your thing. You should know. You should have a quick, snappy answer to this.
Sadly, there is no plan for a Europa lander right
but
now.
2030s. Let's say the 2030s.
That's right.
Would be okay,
ideally,
when it is.
but yeah, we're
And even that does not have a drill that's going to go through the ice. That's going to land on the surface.
That's right. So the pathway is flyby, land, and then get deeper into the subsurface. Before we can do a melt probe or something that gets into the ocean directly, we need to do a lot of ground truth and directly get onto the surface of a world like Europa or Enceladus to see how hard that surface is, what it takes to drill or melt into it, how thick the ice truly is in the region of where we want to someday go through. And I should say that as great as the remote sensing will be, the Clipper mission is a habitability mission. We'll be able to further constrain the ocean chemistry, the ice shell chemistry, and the geology. But unless Europa is extraordinarily generous with her evidence,
which nature sometimes is not,
right, we're not going to find signs of life with a remote sensing mission.
Sure.
To detect biosignatures, you need to get on the surface.
I mean, there is a theory that at least some people have that you could detect really, really complex molecules. And even if you didn't know that they had some particular biological function, you might say there's no non-organic way of making them. Is that something that's feasible with just a Clipper?
That's true. And so Clipper has on board two very capable mass spectrometers, one of which I'm a co-investigator on. And these are really exciting instruments. And we hope to fly similar instruments through the plumes of Enceladus someday. And in both cases, whether it's flying through the plumes of Enceladus or perhaps a plume on Europa, instruments such as those mass spectrometers could give us an inventory of organic compounds, carbon compounds, that provide compelling evidence for a highly selective process that might point to biology. Because really, at the end of the day, biology is selective and abiotic processes for generating carbon compounds is not. So you basically go from a Poisson distribution to a picket fence.
Sorry, this is your fancy scientist way of saying if it's not organic, you'll get a lot of light,
if it's
tiny
not
molecules. If it's not biological, sorry, I use organic in the casual way, but you scientists just mean carbon when you say organic. I understand.
Yeah.
Carbon chemistry. So if it's not biological,
there is a nuance there because carbon dioxide, of course, is carbon chemistry, and that's not organic. So
yeah, okay,
lots of
hydrocarbon chemistry. These scientists, man, this is why I don't want to have scientists on my podcast. They're just too picky. But anyway, you could imagine lots of sort of random, crazy, non-biological chemical reactions that would occasionally spit out a long molecule, but only in the presence of many, many tiny molecules.
Right.
Whereas a truly biological thing might give you this anomalously large concentration of really long molecules.
And coupled with that, so life as we know it, it's really hard to pin down some of the fundamentals of life as we know it. What do we think would be universal? For the most part, the community, biologists, astrobiologists, et cetera, there's a general convergence on biology, however you frame it, is selective. It will form larger molecules by utilizing a pool of smaller subunits. In the case of life on Earth, that is for proteins, amino acids.
RNA, DNA.
Right, exactly. So
not randomly chosen collections of carbon molecules.
Right.
Yeah.
And so if you take RNA, DNA, proteins, and just break them up, you're going to see a pattern that has a fundamental unit based on, say, amino acids linked together, 1, 2, 3, so on and so forth, right? So it's just not a random smattering.
Yeah.
Now back to the alien oceans and having missions that could fly through plumes on Europa or Enceladus. Absolutely, there could be some incredibly compelling evidence. But even after that, you're going to want to land.
Oh yeah, no,
right?
then you're going to want to land more than ever, right?
Yeah.
No, that's true.
And with those chemical analyses, you're not actually going to see the life. You're not going to be able to put that under a microscope until you get down to the surface and grab a scoop of it. And one of the things that makes me nervous about depending on flyby missions for analyzing, say, plume material is the small quantities that you actually get as you fly through a plume. Now, when we talk about flying through a plume on Enceladus or Europa, it's not like flying through Old Faithful up in Yellowstone, right, or even
or the fires here in LA.
Right, or even a snowmaking machine at a ski resort. These plumes at the flyby altitudes of, say, 50 kilometers or so, they're very diffuse. And so you're collecting nanoliters to, on a good day, microliters of sample. Whereas if you're on the surface, you're collecting like a full scoop worth of material.
And it's hard to know what you found. I mean, I was a kid, you were a kid, when the Viking landers landed on Mars, and we all thought they were going to tell us whether there was life. And they did some chemistry experiments, and the answer is, like it's maybe there's some hints, but we don't know.
However, so the Viking was a phenomenal mission.
In the 70s, oh my goodness.
In the 70s. So I like to compare the Viking missions and the incredible achievement of the Viking missions. That's the sort of robotic pioneering work that was done in the 70s. That is analogous to putting humans on the moon.
Yeah.
Right? It's a miracle that NASA did that back in the day. When it comes to Viking and life detection, there's a really important nuance that often gets lost in the mix. And when I talk about Europa lander, Viking often gets thrown back at me from the naysayers who don't like astrobiology or who don't like the search for life. They say, oh, you don't know what you're looking for, and the Viking failed and it killed the Mars program for decades. And that is a tremendously false read of history for a number of different reasons. But scientifically, what's really important to appreciate is that the Viking biology payload was largely designed to look for living microbes.
Yeah.
Microbes that were cooking along, living and breathing, metabolizing.
Eating
exactly.
and drinking, yeah.
Right. And so the Viking lander, again, miraculously scooped up some sample, poured it into little agar plates, little sugar water essentially, and did a host of different experiments looking at consumption of gases, release of gases, some of the gases were isotopically labeled. But all of those results required microbes to actually be living and metabolizing. And as we know, that's hard to do even in the lab.
Yeah.
And so it was a tremendous achievement. But the way in which we search for biology now is to look for the chemistry of life, the structures of life. And on Viking, the measurement, the instrument that kind of put to rest some of the ambiguous results about the metabolic experiments was the gas chromatograph mass spectrometer, which did not detect any organic compounds at the level of parts per billion.
Mm-hmm.
And so the conventional wisdom is, if you ain't got any carbon, you ain't got life,
yeah.
At least in terms of searching for life as we know it. And so the GCMS results superseded any ambiguity on the biology results.
But this gets into what I really wanted to use this opportunity for, is to talk about what life is or might be. I mean, you're looking for life in the solar system. We don't know a lot about what it is. Previously on the podcast, we've had Kate Adamala talking about making synthetic life in the lab. We had Sarah Walker talking about what life is from a sort of information theory perspective. Let's get down and dirty with like the chemicals and what might be going on. So how do you conceptualize what life might be when you're imagining what we should do to look for it?
Yeah, it's a great question with a myriad of ways to answer it. And first and foremost, when it comes to searching for signs of life, be it on Mars, within alien oceans of the outer solar system, on Europa, Enceladus, Titan, etc., or on extrasolar planets, or with SETI signals, I think it's really important to not get too precious about life. What do I mean by that? Well, the search for life comes under incredible scrutiny, sometimes very valuable scrutiny. But oftentimes that scrutiny is disproportionate to the way in which other scientific questions come under scrutiny. And that's in part because we, I think, imbue this question with a certain amount of preciousness.
Yeah. Well, we take the answer seriously. But look, I'm certainly someone who thinks that both the investigation of how life started and our search for it is way underfunded and emphasized within the scientific community. Like,
excellent. So
you're preaching the converted. It's an official Mindscape position that we should spend more money and effort understanding where life came from.
Right. But let me give you an example. In geology, there's the question, what is a mineral?
Yeah. Okay, but fine.
So,
still, operationally, you're building instruments.
Right.
You need an answer, even if it's not the perfect answer.
That's right. So if we can remove sort of the precious layer of how we think about life and biology, then we get to some operational approaches. And fundamentally, life is a layer on top of geology. Life alleviates chemical disequilibrium in the environment to accelerate the increase in entropy. And I don't need to tell you that.
We love increasing entropy. It's our favorite thing.
Right? But to that end, life does it in a very chemically specific way by harnessing the energy available in chemical systems to do work.
The free energy, as we say.
The Gibbs free
Yes,
energy.
That's right.
Exactly. And so that's...
I mean, you and I know what that means, but just to be clear, very roughly speaking, for those of you who have read From Eternity to Here, you know that if a system has energy, you can roughly divide it into useful energy and useless energy, right? The useless energy is just all entropy and temperature. The useful energy that you can do work with, that's the free energy we're talking about here.
Right. And Gibbs free energy, Josiah Willard Gibbs, huge fan. He's one of these vastly underappreciated physicists.
One of the first great American scientists also.
100%. Yeah. And can we divert into Gibbs for
Yeah. We're just these electrons are free.
So Gibbs just vastly underappreciated. He's incredibly humble and just kind of lived a very simple life at Yale. None of the as much as I love Einstein sort of established the crazy physicist archetype, right? Yeah. And so some of that persists, and in order to be a genius and brilliant, you must have something weird about you, right? If it's not the crazy hair, you must have crazy tattoos, et cetera, et cetera. And to me, that's so artificial. Gibbs was just an ordinary guy with great thoughts, and so I find his very refreshing to read about Gibbs. And
we're still thinking about the significance of these concepts for ideas like the origin of life. So you can say, and I will agree, that it makes sense that one of the things life does is turn this free energy into higher entropy energy. It's not completely clear that there's a law of physics that says that should happen, or under what condition it would happen, or is it probable? So that's what we have to sort of empirically figure out.
That's right. And so, let's dive into Gibbs free energy for a minute. So, as you said, you can think about energy in a couple of different ways. The heat and change in entropy. Can't get much done with that. And then there's the work. And oftentimes when we think about work, we think of PDV, pressure and change in volume. Or
there's a piston, we're pushing it in there, it pushes back, we're doing work.
Or, to go to Physics 101, we can think of work as force times distance. And force, of course, is MA or mg in the case of planet Earth. And so when we think about the work done, we can think of mgh, mass times the gravitational acceleration times the height to which you hold something and then drop it. Well, Gibbs had this great insight in that, within chemical systems, there should be some chemical equivalent to mechanical work. And that chemical equivalent comes with something like chemical potential.
Right.
And that chemical potential times the change in mass of a given compound within a system yields you some of that energy available to do work.
So can we think of this as, if you have hydrogen and oxygen in a bottle, it has the ability to light on fire and do some work?
That's right. And so Gibbs' brilliance, right? So entropy is how do you think about aggregations? Right? Where do things aggregate? And Gibbs obsessed over this. He was, thankfully so.
For us.
Clausius and Boltzmann, et cetera, had preceded him. And so he basically said, well, this aggregation and the pressure and volume changes, that's missing a certain aspect of how we do the full cost accounting for energy and changes in energy. And Gibbs said, well, you know what? If I have something like hydrogen and oxygen, these two parts, and he loved to use this term, new parts, right? So there are these new parts that get created from old parts. So hydrogen and oxygen come together to make water. And so in any given system, you might have the initial parts some compounds, and then at the end you have new parts. And so his addition to the energy equation, which folds into Gibbs free energy, is that chemical potential for each compound, for each chemical in that system to then react with other compounds and to form new parts.
Mm-hmm.
So he really helped complete the full accounting for the conservation of energy.
Okay, but we got to get from here to life somehow.
Okay, right. So
I gave you that digression.
But it's beautiful physics. Isn't
Beautiful
it?
physics, and I love it, and I could go on. We all like learning new things. The real problem is there are too many things out there to learn. Not only does it take time to learn any one of them, but you have to choose which is the most interesting thing to dive into. Blinkist is an app that will help you out with this. It's basically a way of boiling down nonfiction books and condensing them into just 15 minutes worth of reading. You can read it, get the general idea and move on, or decide that you want to dig in more deeply. That's what I really like about it. Not that it's a replacement for books, but it's a way to decide which are the books that you really want to devote the time to. There's a set of wonderful titles they have, such as The Biological Mind by Alan Jasanoff, Digital Darwinism by Tom Goodwin, or The Science of Storytelling by Will Storr. Right now, for a limited time, Blinkist has a special offer just for Mindscape listeners. Go to Blinkist.com/Mindscape, and you get to try it free for 7 days and save 25% off your new subscription. That's Blinkist, Blinkist.com/Mindscape to start your 7-day free trial and also save 25% off, but only when you sign up at Blinkist.com/Mindscape.
Okay, so back to life and why the heck life arises. And here I'm talking just about life as a chemical system.
Yep.
Certainly there is life in silico. It's all sorts of kind of broader
artificial
ways.
versions.
But strictly speaking, for life as a chemical process that we currently call biology, I think it is, if you allow me to use a loaded term, I think it is motivated by that requirement of the universe to increase entropy, and in so doing, alleviate chemical disequilibrium in the environment.
Yeah.
And so any place where you've got Gibbs free energy available, enzymes, and how you get to an enzyme is tricky, but enzymes allow you to overcome a bit of a hump to then release that stored chemical energy.
Right. Metaphorically, it's like the spark that could light the hydrogen and oxygen on fire, right? There's
right.
some ability for entropy to increase lurking there in the chemicals all around you, but you have to allow it to get there somehow. And that kind of enzymatic process is what you're saying leads to life? Is life adjacent?
That's right. And so there are numerous hypotheses for the origin of life itself, but I think one of the most compelling suspects in the story of how life arose, perhaps on Earth and perhaps elsewhere, is the reduction of carbon dioxide. How do you take carbon dioxide and pull off the oxygens and do something else with it? And sometimes this folds into the acetyl-CoA pathway that is part of modern biology.
I'll take your word for that.
But early on, minerals may have been the sort of first catalytic environment that were kind of the proto-enzymes that allowed for the reduction of things like carbon dioxide to then form organic compounds, and then to be a template for self-replication and eventually the formation of vesicles that would someday be called cells.
Yeah. I mean, I don't want to get too deeply into this because we got to talk about various moons in the solar system. But I mean, maybe the quick overview of metabolism, replication, compartmentalization, the most important ingredients for life.
Well, so I'm a metabolism firster. And I think that, and that's where Gibbs free energy comes into play. You need a motivation for the energy dynamics of life.
Why don't you tell us the opposing school of thought?
Well, I don't think it's so much opposing. It's just a lot of different camps are trying to figure out where the intersection of metabolism, information storage, and compartmentalization all come together.
Everyone agrees you need these three things.
Exactly.
People put different emphases on what is the crucial step.
Right. And
but replication and information seems to me, from my reading of the community, to be the thing that most people are focusing on, whereas you're saying you're a metabolism kind of guy.
Right. Now the information molecule side, what many of us like to call the top-down side, is kind of low-hanging fruit. We have the information molecules.
We know what RNA and DNA are. They're in us now, right?
And so we can look at the RNA world, the idea that the earliest information molecule was some form of RNA or polynucleic acids, PNAs, et cetera. But the ladder down stops at those PNAs.
You mean down to simpler and simpler things going on?
Right. So top-down approach, you can climb all the way down to polynucleic acids and variations therein. But how do you actually bootstrap from?
Where do you get them from? Just from chemicals sloshing around in a warm small pond.
Right.
Yeah.
And so as much as I love the Miller-Urey experiments,
which were?
Getting amino acids and some more complex compounds from a spark discharge experiment that had some pretty simple compounds like methane and water and ammonia in it. You then get amino acids and some of the building blocks of life. Amazing, right? Just mind-blowing back in the 50s.
And this is the 50s. And so as I recall, that was, basically the conclusion is it's not that hard to make amino acids out of random junk.
Right.
And they thought, well, tomorrow we'll do proteins and then we'll do DNA, but that
before long, a little mouse is going to run out of the lab.
Yeah, exactly. Much harder.
Right. And it's from that progression in the 1950s to now, where, of course, we've had the genetic revolution. Leslie Orgel and others really spearheaded the RNA world, and that was phenomenal work. And then in 1977, going back to Viking, right? So a year after Viking lands, hydrothermal vents are discovered.
Here on Earth.
Here on Earth.
Not on Mars.
No. Right. Or Europa for that matter.
Yeah.
But so much happened in the late 1970s. It's just one of my favorite scientific periods. So hydrothermal vents are discovered.
Under the oceans? Tell us what a hydrothermal vent is and why we care.
So hot springs at the bottom of the ocean. New oceanic crust is forming, or fractures in the oceanic crust are allowing chemical reactions to proceed that drive hot water and all sorts of interesting chemistry. And so part of what was exciting about the discovery of the hydrothermal vents is that along with the astonishing ecology, the biology that was found there, the tube worms, the zooarcid fish, the mussels, etc., these also started to become recognized as cauldrons for interesting mineralogical and potentially organic chemistry to serve as a place where processes perhaps related to the origin of life could occur.
And part of that is simply, life is dynamical. You're not going to imagine that life forms in something that's just sitting there stationary. You need some shake-up, something that is knocking things around and hopefully falling into good patterns.
Right. And one of the things that I do like about the hydrothermal vents model for the origin of life is it's motivated by a metabolism first approach. You've got compounds coming out. The fluids are full of things like hydrogen and methane compounds that have electrons they just want to give away.
Energy.
Energy, coming back to Gibbs free energy, right? And there are minerals that also want to give away electrons, and the ocean around it wants to accept those electrons. So there's a lot of really compelling chemistry that occurs around hydrothermal vents. The downside, and the argument that's often put against hydrothermal vents, is all that damn water.
And water is not deadly. I mean,
right. Well, but it is to certain chemical reactions, right?
Sure.
So when you link two amino acids together, that process, that polymerization, spits out a water molecule. So if you're linking two amino acids together in a liquid water environment, you're trying to introduce a new water molecule into a place that's full of water molecules. That's not particularly advantageous.
Right.
Chemistry doesn't like to proceed in that direction.
Yeah.
And that's where many of my colleagues who do brilliant work on like warm tide pools on the flanks of some ancient continent where you can lap up some primordial soup and then it gets baked in the sun and desiccated. You know, that desiccation process, that's a much better environment for concentrating things and linking things together. Like
and they showed it on Star Trek that was how life formed here on Earth.
So it must be true.
Yeah.
Right. So those are kind of, there are different camps as far as information first, metabolism first, compartmentalization. And then layered on top of there is a Venn diagram of environments that we see here on Earth. Hydrothermal vents, tide pools, hot springs, other things. What I find so exciting about these alien oceans beyond Earth, these worlds like Europa, Enceladus, and Titan, is that we can just do this experiment.
Yeah.
Right?
Well, we've done it a handful of times. Let's put it that way, right?
What do you mean we've done it?
I mean, the solar system has done it.
Exactly. Right. So the solar system is running these experiments.
Yeah.
We can go into our own backyard, our own solar system backyard, and just look in the ice and in the oceans of these ocean worlds of the outer solar system and say, hey, you got life? Did
Yeah.
life originate there?
Yeah.
And I do think these worlds are great places for second independent origins of life.
So let me see if I have the picture. I mean, we know that certain things are necessary: the compartmentalization, the replication, the metabolism. We know they're all necessary, but we don't know the order or what led to what or anything like that. There's various hypotheses. And part of the problem is, even though we have a lot of life currently on Earth and even very simple organisms, it's still a stretch to say what the first organisms were like, right?
That's right.
Like, we can't definitely say that. So if we were able to look at other environments where there was also the possibility of these things going on, we could learn a lot.
That's right. And this is where it's just beautiful. We have a chance to look at what is contingent and what is convergent in biochemical evolution. Is DNA, RNA, and protein chemistry the only game in town?
Yeah.
If you run the clock again, does biochemistry converge on that solution?
So what's the answer?
We got to go to Europa.
No, but what do you think? Do you think that DNA is necessary for life?
So here's what I can say with confidence, that I love Mars. I love doing Mars exploration. It's a beautiful world.
But
there are two things. First and foremost, our search for life on Mars is primarily a search for life in the past as preserved in the rock record. Mm-hmm. And large
because there was running water on Mars,
right?
But there's
Mars
not now.
had a wet and watery past, a warmer past, and we think that Mars was definitely habitable. And I, for one, think that Mars most likely had life. Based on what I know of life on Earth, I would predict that if the origin of life is easy, it's
a big if.
Big
Yeah,
if,
okay.
right? But if you grant me that, then Mars had life, and there should be evidence of life on Mars.
Yeah. I would argue that we have strictly zero information about whether it was easy or
100%.
hard, because our existence does not count.
That's right. But what's the best way to get to turn that from zero to non-zero.
Right. Look somewhere else where there was one.
Exactly.
That's right. Okay, but you did say you bet that Mars probably had life. But you think we have a lot of evidence that it had the conditions.
Right. Now, the problem is that, let's say we go to Mars and we find some beautiful rocks, some beautiful stromatolites, rocks that preserve perhaps the microbial fabric or fossils. DNA, RNA, large information molecules do not last for a long time in the rock record. Now, in the subsurface of Mars, there could be living life, and I would be thrilled to go and explore Mars for that. But even if we found DNA-based life on Mars, Occam's razor would still tell me, I can't quite count on that as a second origin.
Right.
Because Earth and Mars...
Too close.
Too close. Neighbors, planetary buddies, just sending stuff back and forth.
Swapping bodily fluids.
Yep, throwing the baseball, asteroid impacts.
And in fact,
stuff.
we have, meteorites from Mars here on Earth, and people look for evidence of life in them.
Exactly. This isn't just speculation. We actually have examples. The outer solar system is much harder to, say, contaminate with Earth rocks or Mars rocks. And so if we went to Europa or Enceladus or Titan with a robotic vehicle and we found DNA-based life, that to me would strongly point to a second independent origin with a convergent biochemical evolution towards DNA. And that would be phenomenal.
Can you name at least one plausible alternative to DNA?
No.
Okay.
No, I wish I could.
But we admit that might just be our lack of imagination.
That's right. Now, Steve Benner in Florida has done some beautiful experiments on adding additional base pairs. So there are some interesting synthetic biology experiments that have been done.
I've heard about it. I think the Kate Adamala also talked about this. Yeah.
Yeah.
So the GCTA might not be the whole alphabet.
That's right. It's not the whole alphabet in terms of you can push, at least in the lab, the DNA molecule to have added base pairs. Is that biologically acceptable?
Yeah.
We don't know those experiments. It hasn't gone from cool chemistry to actual biology, but it's really compelling.
Okay, so we will at least have the ability to ask. So there's one thing that we could learn. I mean, obviously, the fact that if we learn that there's life elsewhere, that's the big thing. The second thing is it DNA, RNA, similar kind of chemistry? I'm sure that some people in the audience are thinking, isn't it too cold out there to have life, way beyond the orbit of Mars?
Yeah.
Why are we even talking about these moons?
Right.
They're not in the Goldilocks zone.
That's right. So this comes back to the fundamental game-changing aspect of these ocean worlds beyond Earth. Europa, Ganymede, Callisto, 3 moons of Jupiter, Titan and Enceladus, 2 moons of Saturn, and even Neptune's curious moon Triton. These are worlds where liquid water is maintained and sustained in large part through tidal dissipation, tidal energy, pumping and stretching and heating these worlds from the interior.
Because these moons are orbiting humongous planets.
Exactly. So everybody knows and loves the tides on Earth. On Europa, you're dealing with Europa is about the size of our moon, but Europa is orbiting Jupiter, which is some 318 times as massive as the Earth. And Europa is just getting tugged and squeezed like a ball of taffy. And the predictions are that if you stood on Europa, you might rise and fall in the diurnal cycle, the daily up and down, which is equivalent to 3.55 Earth days. You might rise and fall with the tides about 30 meters or nearly 100 feet per Europan day.
All right, so take your Dramamine if you're going to visit Europa. But so that's injecting a lot of energy into the ice.
Right.
It would be almost crazy to think that some of it wouldn't heat up and make a liquid water ocean.
That's right. So the traditional habitable zone, the way we normally thought about planets in the early days of astronomy and planetary science, was that The habitable zone is defined by the distance from your parent star, and habitability was conceived of as having a liquid water ocean on your planet's surface in contact with a nice atmosphere, and then you're off to the races.
Yeah.
And in that kind of conception of the habitable zone, you had this, at least in our solar system, Goldilocks scenario, where Venus, Earth, and Mars were kind of like those little bowls of porridge in the Goldilocks story. Venus is too close to the sun, gets too much energy. Any water that it once had got baked out. It's too hot. Mars, too far away, too cold. Any water that it once had froze out. Now, the story of Venus and Mars is much more complicated.
Turned out to be more complicated.
Right. So,
atmospheres matter.
Right. And they at points in the past did have liquid water. But at least in the modern epoch, planet Earth is in that Goldilocks zone where it has liquid water on the surface in contact with our nice thick atmosphere. And the reason we have that ocean, our ocean, is because of energy from the sun, from our parent star. What these ocean worlds of the outer solar system are teaching us is that there's another way to get the business of maintaining and sustaining liquid water done. Tidal energy dissipation, and in part coupled with radiogenic decay, in other words, the decay of heavy elements, uranium, thorium, even potassium, provide enough internal heat so as to keep some liquid water liquid. And on Europa, we think that the tidal energy dissipation could lead to an ocean, a global liquid water ocean of some 100 kilometers in depth. That's 60 miles in depth. That's 10 times the depth of the Mariana Trench, the deepest region in our own ocean. And so that tidal energy is really changing the way we think about habitable environments in our own solar system.
Would it almost always be the case that throughout the universe, not just the solar system as we know it, these kinds of oceans, so basically there's two possibilities. One is you're heated by the star and you're like the Earth. The other is you're a satellite of a giant planet, and regardless of what the star is doing, you're heated by these tidal stresses.
Yep.
Would that second option always come with an ice sheet around it?
Yeah, so for the most part, the answer is yes. I'll get to Titan in a second because Titan also has an atmosphere. But I do want to give the heavy elements the credit that they're due. And radiogenic decay can last for a long time. Pluto, and we're still kind of understanding Pluto as this beautiful dynamic world. Who cares if it's a planet or a dwarf planet or what have you? I just love it as a world. Pluto may well have a liquid water ocean, perhaps with some ammonia or other antifreeze mixed in. And if Pluto does in fact have a liquid water ocean, it is sustained through the trickling out of heat from the decay of these heavy radiogenic elements. Coupled with that, there's interesting thermal physics associated with ice shells. All of these ocean worlds rely on ice being a good insulator. Ice is a great blanket. But there are different kinds of ice that serve as better blankets than others. And so on Europa, Enceladus, that's ice one, ice that we can grab out of our freezer,
yeah.
the sort of traditional ice. And if you've ever built a snow fort or walked into an igloo or something like that, you know that you can actually stay pretty warm if you're surrounded by frozen water.
I'm told that it's the snow that does the insulating, not the ice.
Well, yes, but even ice itself.
My vast igloo experience coming in here.
Yes. So snow, the porous material, is definitely better, but even ice itself is
Okay.
not
Gotcha.
is not a tremendously good conductor of heat. But then there's this other aspect, clathrates. So a kind of ice that reconfigures to trap various molecules. Clathrate means cage or to encage. So on Pluto, The ice of Pluto, the water ice, is mixed with nitrogen and methane and perhaps some ammonia and stuff. And that mixture may help Pluto have a better thermal insulation to keep its ocean from...
There could be life on Pluto, is what you're telling me?
Well, so, okay.
If we let ourselves dream a little bit?
Right. So no.
Because I saw the Rick and Morty episode. They're very upset that they've been demoted from planet status.
Oh, I have not seen that. But so where Pluto kind of falls short is in the way I like to frame this is the keystones for life are you need liquid water, you need the elements to build life. And to the best of our knowledge, life as we know it at least needs a smattering of 54 elements from the periodic table. The most significant of which are the chnops, the carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Then you need iron and some heavy elements. And then the third keystone is you need some energy. And that comes back to the Gibbs free energy. You need some chemical disequilibrium. Europa and Enceladus and perhaps even Titan, I think, satisfy those three keystones. I think the oceans of Europa and Enceladus are mixing with a rocky seafloor. That rocky seafloor gives rise potentially to hydrothermal vents, which gives rise to the elements needed to build life and the energy needed to power life. Pluto might have a lot of the compounds and water needed for satisfying the liquid water keystone and potentially the energy keystone. Methane, as I mentioned, is a good molecule, and so life could eat or make that. But part of what I worry about with Pluto is whether or not it's got enough of the heavy elements, whether or not it's got enough of the
it's so
rocky
tiny.
material. Yeah. But its density is sufficient to indicate that there's got to be some rock fraction.
You seem to hint that Titan was a weirdo also.
Titan is my favorite place to search for weird life.
Weird life.
Life unlike life as we know it.
I'm going to qualify any life that is not on Earth as pretty weird, but you mean substantially different.
That's right. So, and here's where, coming back to kind of an operational approach to searching for life, here's where we can start to slice and dice things in a very pragmatic way. When I look out at Europa and Enceladus, and Titan also has a liquid water ocean beneath its icy shell, and that ocean may be mixing with rocks. I can generate an hypothesis about the prospects for carbon and water-based life out there in our solar system.
Right.
And that hypothesis is founded on observations of life here on Earth. So life on Earth is water and carbon based. Water is the solvent. Carbon is the key building block. And we can look at all the extreme environments on Earth, Antarctica, the hydrothermal vents, et cetera, and say, okay, water and carbon based life is tenacious as...
There's always a little bit of life everywhere
right.
on Earth anyway. Yeah. I mean, I do, whenever people say that, I feel like raising my hand and saying, it's not equally hospitable to life, all these different environments, right? I mean, there's less life
That's right.
in the desert in Antarctica than there is in the rainforest.
100%.
Okay. But there's a little bit of life. There's a little microbial life everywhere.
That's right. And please be aware that oftentimes when I talk about the search for life and life on Earth, as beautiful as the penguins were in Antarctica or the giraffes of the African savanna are, et cetera, multicellular life, metazoans, these larger creatures, are boring as hell. and the reason for that is because we all just represent the tiniest of twig on the vast genetic tree of life.
Yeah, not a lot of diversity within
Right.
the metazoans.
For all of the shape diversity, we all are heterotrophs. We eat carbon compounds and breathe oxygen to essentially do a fancy campfire burn.
Right.
From penguins to sea slugs to giraffes, we're all doing the same metabolic process.
Whereas microbes,
holy cow. They have figured out a way to eat anything and everything, from acids to bases to, and doing it at high pressures, low pressures, you name it.
Which is extraordinarily reassuring for the search of life, for life elsewhere.
Exactly. And so when I talk about the diversity of life on Earth and how we use our study of life on Earth to provide a bridge for assessing habitable environments beyond Earth, it's in that microbial context.
Mm-hmm. Okay.
So
we're not going to find penguins on the ice shelf of Europa.
Well, they're birds. I mean, come on. I wouldn't rule out octopi or things like that.
Don't distract from Titan. We're going to get into the weird life.
So we can make an hypothesis about water and carbon-based life on Europa and Enceladus and even within the water ocean of Titan. And that water and carbon hypothesis is rooted in our understanding of how microbial life works on Earth. Those oceans, if you transported microbes on Earth to those worlds, the evidence that we have today would indicate that those microbes could survive. So we can design spacecraft to test that hypothesis of water and carbon-based life. Water is the solvent, carbon as the building block. Titan, along with having this deep ocean beneath its icy crust, also has this crazy methane cycle. The surface temperature and pressure of Titan. So the atmosphere is thick on Titan. It's primarily nitrogen. But the temperature and pressure of Titan is such that methane exists in all three phases. Solid, liquid,
triple point.
Triple point, exactly. So solid, liquid, and gas. Similar to where Earth resides in terms of its surface being at the triple point of water. And so Titan's got these seasonal cycles going on, and it's raining down methane and ethane and potentially larger organics. And on its surface, the Cassini spacecraft helped reveal all of these methane-dominated lakes and seas. And this is where things get weird.
A lake of methane.
A lake of methane.
It's already pretty weird, yeah.
Yeah, and so could you have weird life on Titan where the solvent, the thing that the parts of life get mixed and combined in on Earth, that's water, where the solvent is liquid methane? I don't know the answer to that question.
Yeah.
Nobody really does.
No.
Chemically, the difference between liquid methane and liquid water is that water is a polar solvent and methane is nonpolar. Water molecules have a slight positive and negative charge on them due to the way in which the electrons arrange themselves in the two hydrogens and oxygen. Methane does not have that.
Methane is like a perfect little tetrahedron.
Yep. Kind of. Yeah. And so in chemistry, like dissolves like. So water is very good at dissolving other polar compounds. That's in part what allows the chemistry of our biology to work. And of course, as you know from mixing oil and water, oil is, for the most part, nonpolar, and it
separates out. Yeah, right? And that's kind of useful.
That's kind of useful, right? Now, if you flip the tables and have a nonpolar solvent like methane, could you get enough interesting chemistry done to really drive biochemistry?
Yeah.
There is water there.
It would be different.
It would be different. And thankfully, last summer, if my memory serves, everything's a blur, NASA selected a mission to get back out to Titan. It's this phenomenally exciting mission called Dragonfly, PI'd by my friend Zibby Turtle, and it's out of the Applied Physics Laboratory in Maryland. This is a mission which hopefully will launch in the mid-2030s. I'm sorry, it'll get out to Titan in the mid-2030s.
Okay, I was going to say, that's way out there. It's hard to plan that far, but okay.
Too many missions. So it gets out to Titan in the mid-2030s, parachutes down through the atmosphere, gets rid of its heat shield and all that, and then starts turning on these rotors. So just like the quad drones that you see, and somewhat annoyingly,
we're sending a drone to Titan.
Right.
Yeah.
So we're sending a drone.
We're sending one to Mars also, I know.
That's right. Now the Mars helicopter has got, it's just got one set of rotors on it. The Titan Dragonfly mission is much larger. It's the size of a dining room table. And along with looking at the geology and geochemistry of Titan, looking at the dunes and all of the interesting things that are happening in the world of Titan, we're also going to be looking for signs of life.
If it gets shot down by ornery locals, that'll be a great success, right?
As long as we get a picture of them before they shoot.
Yeah, there's a camera on the drone, I hope, right?
So it's just a beautiful mission, and what's fun about Titan, my friend and brilliant scientist and engineer Ralph Lorenz has done this calculation where, if you could survive on Titan as a human, a lot of caveats there.
Yeah.
And kind of have your own Icarus wings, you could fly.
You could fly because of low gravity, thick atmosphere.
Exactly.
I'm glad that calculation was done. Yeah, taxpayer dollars at work.
Yes.
Good.
So, but that in part helped lead to the viability of doing a rotorcraft mission that would land on Titan and search for signs of life.
Wow.
Now, primarily with that mission, and I'm a co-investigator on that mission, we'll be looking for evidence of perhaps water-based life that has been erupted from below. Mm-hmm. But we'll also have our eye towards the discovery-driven aspect of science.
Yeah. Who knows, right?
Yeah. What if there is life that has originated and evolved in these ethane-rich lakes?
Is the trick that we don't even know how to look for that? So, I mean, we have to design an experiment that's actually looking for certain chemicals.
Right. And here again, we come back to that issue of specificity, life being very selective. We think that even if life is based on some chemistry unlike life as we know it, even if life is weird compared to the liquid water and carbon-based life that we know, it will still have that selectivity and specificity where it is built on fundamental chemical units.
It'll like certain molecules more than others.
Right. And so if you do an inventory with something like a gas chromatograph mass spectrometer, you might see a pattern, even in weird life, that distinguishes it from kind of the abiotic processes that are just random and kind of linked together atoms by atoms.
I suppose we should put in a word for Enceladus. That's the other place we
Enceladus is phenomenal.
Yeah. I mean, when I hear people talk, they're more. I mean, there are certainly people who think that of all these, Enceladus is the one that is the most likely to have life. I know you might not be in that, but there are Enceladus partisans.
100%. And like these worlds are all beautiful and meritorious of exploration.
Like your children, yes. You love them all.
Enceladus, just to calibrate, Enceladus is the new kid on the block, the new shiny object, right? And so the Cassini mission just ended, and we have a lot of new data on Enceladus. And so there's a lot of excitement about Enceladus. And Enceladus was very generous. Wonderfully so. So Enceladus, coming back to Europa and the discovery of Europa's ocean, that took that kind of detailed physics. The Galileo spacecraft did not observe any plumes erupting out of Europa's ice shell. We now think we've got some curious evidence using the Hubble Space Telescope and some Galileo data for water-rich plumes coming out of Europa. But when Cassini flew by Enceladus, bang, there it was. These plumes erupting out of the icy surface of Enceladus. Now, initially, skeptics, myself among them, viewed those plumes as perhaps just a devolatilization of the ice and clathrates, perhaps, and other things. We see jets of material elsewhere in our solar system. We see comets
Sure.
producing jets. So early on, some of the evidence for Enceladus could have been explained by these plumes being analogous to cometary jets, where something's just causing outgassing. But as the Cassini spacecraft flew by and tasted the plumes of water, it also revealed that the plumes have methane and carbon dioxide, a smattering of organics. And for me, what really turned the tide was the discovery of salts.
Okay. What's the definition of a salt?
So a salt, something with cations and anions. Traditionally, think of salts as like sodium chloride, potassium chloride, magnesium chloride, magnesium sulfate, all sorts of stuff where you can take a positively charged cation and combine it with a negatively charged anion. So
that means the life would be tasty.
Well, no. So why are salts significant in terms of evidence for an ocean? On Enceladus, if you just had water in the plumes of Enceladus, and water mixed with carbon dioxide and methane, and even small organics, those are all things that we see in comets.
Mm-hmm.
Okay.
So no biggie in some sense.
No biggie in some sense. Now, still very exciting.
Still cool, but
right.
yeah. But we see them there's a trillion comets in the Oort cloud.
Exactly. And comets, the way we get those compounds like methane and some of the organics is through the ice having things like methane and potentially ammonia, and then it gets photolytically processed. UV light from the sun processes it and produces these larger organic compounds. So at Enceladus, you could be very conservative and say, no, this isn't evidence of an ocean. This is just photochemistry combined with some devolatilization of the ice shell. But with salts, we don't really see salts on comets.
Right.
Salts are a harbinger of water-rock interaction, liquid water leaching through silicates.
Right.
So for me, when the cosmic dust analyzer on Cassini returned evidence of salts, that was okay. Now,
So it's a sign of water, not a sign of life. But once you have the water, then maybe it's life appropriate.
right. And so for me, the Cassini observation of the plumes and identifying that the plumes of Enceladus have salts, that gives me a large degree of confidence that we're actually sampling plumes that are connected to a liquid water ocean below.
And do we have evidence that there's an icy crust on the top?
Of Enceladus? Yeah, absolutely. That goes back kind of to the first piece of the puzzle, analogous to Europa. And I should, of course, mention that for both Europa and Enceladus, the geology of the icy surfaces point to very, very young ice.
Which is good because...
Right, something has to be resurfacing this material. Some sort of geological cycling of the ice with something below repaves the ice of Europa and the ice of Enceladus to give you a surface with no craters.
Right. So it's not quiet.
It's not quiet, right. Now, at Enceladus, there's as the story would unfold from Cassini, additional evidence would corroborate the ocean hypothesis. The moving of the ice shell, a decoupled ice shell, a shell that is kind of free-flowing and disconnected from a rocky interior. That was observed on Enceladus.
Oh, okay. I didn't know that. So that really cinches the deal in some sense.
Yeah.
There's got to be some liquid layer in between the ice and the rock.
Right. And then there's also evidence of hydrogen and other things that actually point to potentially active hydrothermalism, active hydrothermal activity within Enceladus. Even things like silica nanograins have been discovered.
So the people who are very excited about Enceladus are not just whistling Dixie. I mean, there's a lot of...
And I'm incredibly excited about Enceladus. Here's the rub on Enceladus, though. If you kind of do a one-for-one comparison with Europa. So,
keeping in mind we're talking to the PI of the Europa lander.
well, not a PI because the Europa lander isn't the Europa lander's dead.
Okay.
So
Oh, it's dead?
well, it's a technology development effort. It's not planned to go to the launch pad. In order to get it to be alive.
But you're a Europa guy.
Yes, but I'm an Enceladus guy too. I've published on Enceladus, not as much as Europa, but just doing a full calibration.
Yep.
Europa is 3,000 kilometers in diameter. That's about the size of our moon. It's a moon that we understand very well. Very well, given the data available. We think that Europa has been around for the history of the solar system. We think it formed around Jupiter as Jupiter was forming. And we think that the ocean itself of Europa has been there for the history of the solar system.
For billions of years, yeah.
Now, coupled with that, there's some interesting chemistry that occurs within Europa's ice shell and Europa's ocean, and we'll hopefully get to that. But Enceladus, when it comes to this issue of time, I mentioned the keystones for habitability, liquid water, elements, and energy. A fourth, potentially fundamental keystone is time. How long has that convergence of keystones been around? Now, that may not be important. It may be that life arises very quickly. But if I were a betting man, I would kind of...
More time, the more chances, right?
Yeah. And so Enceladus, there is a significant debate within the planetary science community right now about, first and foremost, what makes Enceladus tick? What's the full tidal energy evaluation for Enceladus? And how long has Enceladus and its ocean been around? And part of the kind of thread that people have pulled on is the rings of Saturn. Rings are not particularly stable.
Right.
So the rings of Saturn, according to some, they're again, this is a heavy debate. It's a wonderful debate. It's a beautiful debate. This is why we love doing what we do. But there's a camp in the Saturn community that says the rings of Saturn tell us that something big happened not too long ago, because otherwise those rings should have either collapsed, been pulled into Saturn, or been kind of orbitally evolved out of Saturn.
Not too long ago, might be millions of years. Not
tens of millions of years, 100 million.
It's not just a few decades ago.
That's right. So the time scale is geologic and astronomical. But some of the hypotheses are that maybe the rings of Saturn were created 100 million years ago by a Kuiper belt object, a Pluto-size object, careening into Saturn and hitting a large moon, breaking it up, creating the rings and a bunch of the small moons, et cetera. And so there is a camp that says that the rings of Saturn are young, and potentially some of the smaller moons, including Enceladus, could be quite young. And if Enceladus and its ocean are young, then, I kind of view Enceladus as this like fizzing Alka-Seltzer tablet that's perhaps doing incredibly interesting chemistry. But I kind of am a little more interested in a stable world like Europa that we know has been around for a long time.
And this is good, the issue of time, because I would like to put everything in a bigger context here. I mean, I think that our listeners probably are happy to say that microbes are awesome, but what they would really like is little aliens flying around in spaceships.
Right.
And we're not going to find that in the solar system, I think is most likely, but maybe elsewhere in the universe. So what can we learn from looking at these other places in the solar system that might tell us something about the likelihood of life multicellular life,
Yeah,
intelligent life, technological life elsewhere in the world?
Right. So this is a great question that actually folds into the second aspect of Europa and Enceladus, and some of the chemistry that I find very compelling about Europa that is potentially lacking at Enceladus. And this comes back to Gibbs free energy and redox chemistry, the coupling of reductants with oxidants. And we touched on this earlier. A reductant is a compound that wants to give away an electron. An oxidant is a compound that wants to accept an electron. And the way I like to think of it, my background's in physics, and it's just biochemical batteries. You connect the positive and negative terminal.
Let the electrons flow.
Exactly. So life alleviates chemical disequilibrium in the environment the same way that when you buy a battery at a corner store, that battery will store energy for a long time, and it'll eventually trickle out. But you can put that battery in a flashlight. You can connect that battery to a circuit and allow those electrons to flow. And in so doing, you get work done. You get the work of shining a light on something or running a little remote control car or what have you. And the battery runs out a lot faster because you've completed the circuit. Biology does that in our environment. Around Earth, there are all sorts of geochemical batteries.
Right.
And the microbes tap into that.
Who was the biologist who said that life is just an electron looking for a place to rest?
I don't know, but whoever.
That's a good quote. Yeah, that's true.
Brilliant. Yeah. My friend and colleague Everett Schock loves to say that the energy is like being paid to eat a free lunch, and so you're getting energy out of this chemistry that's available in the environment. And so, why is this important? How does this tie back to your question of squid in Europa? Another aspect of what intrigues me about Europa potentially being a better place to search for life is the chemistry of Europa's ocean. Hydrothermal vents, active seafloors are great places for reductants. We see that on planet Earth. Hydrogen, methane, etc., pump out of our seafloor. And microbes love the reductants, but if all you have is the reductant, if all you have is the negative terminal on the battery, the circuit's not complete.
Nowhere for the electrons to go.
Nowhere to go, right? So you need an oxidant. You need a source of oxidants. And on Earth, a lot of the oxidants are things like oxygen and sulfate, et cetera, and we've got tons of oxidants. On Enceladus, it's not clear to me that it has a source of oxidants. So it could have an active seafloor pumping out the methane and hydrogen, but if there's no good source of oxidants, then it might be kind of game over from a Gibbs free energy standpoint, from a what life can utilize standpoint. Europa has this beautiful but also somewhat frustrating surface environment where, by merit of being embedded in Jupiter's magnetic field, Europa's icy surface is being bombarded by charged particle irradiation. Electrons, energetic electrons, tens of keV to tens of MeV electrons, ions, protons, etc., are careening into Europa's surface ice. And that radiation chemistry, that radiolytic processing, is splitting apart water in the simplest case, splitting apart H2O into things like H plus OH. Some of the H escapes, some of the hydrogen escapes. And OH can combine with another OH to form H2O2. What is H2O2? Hydrogen peroxide. Exactly the same stuff that you buy at a pharmacy to disinfect a cup. We know, thanks to Bob Carlson and colleagues and the Galileo spectrometer, that hydrogen peroxide exists within the surface ice of Europa. Further to that, we also know that, thanks to observations by John Spencer and Wendy Calvin using ground-based telescopes, oxygen, O2, exists within the ice of Europa. And we know that things like sulfate and other very useful oxidants exist within the ice of Europa, in large part from that radiation processing.
Mm-hmm.
So if the ice of Europa is getting mixed into the ocean below, you now have this beautiful scenario where the radiation and the radiolytic processing of the surface ice creates that positive terminal of the biochemical battery. So if the oxygen, peroxide, sulfates, et cetera, get mixed into the ocean, they could be combined with reductants from the seafloor to help power life.
Yep. Okay.
And so people often say, well, isn't the radiation of Europa's surface problematic? Isn't it going to destroy evidence for life? Isn't going to make landing there harder? Yes and yes. But the upshot of that radiation is that it could also be central to that third keystone of life, the energy component of life. And sulfate, microbes love sulfate. But as I mentioned, oxygen is also present in Europa's ice. Oxygen is critical to the emergence of large multicellular life on Earth.
Okay, wait, that was a big leap you just made there.
Yep, good. So,
I mean, don't we first need to make nuclear cells? Like, aren't there, like on actual Earth, life happened pretty quickly. Multicellular life took forever.
well, I mean, I don't know if it happened quickly. So we know that life arose. There's debate about this, but some say that the first evidence for life is at the sort of 3.8 billion years ago point in time, which would put it about 700 million years after the origin of the planet itself. 800 million years, somewhere in that range. More convincing evidence is available at 3.5 to 3.2 billion years ago. But then multicellular life that utilizes oxygen, that doesn't emerge until about 700 million years ago, 650 million years ago, 600 million years ago.
Yeah.
And
Took 3 billion years.
Right. And so
of little microbes bumping into each other.
That's right.
I don't want to get together with you.
And so there's this long period of those early metabolisms, and then the evolution of photosynthesis, and the people love to talk about life as Darwinian selection and survival of the fittest, et cetera, predator and prey and all that. That's all well and good, but I also like to say that life is also largely about acquisitions and mergers, the symbioses that take place, right? Yeah. And, it's just somewhat similar to economics.
Could you say it's about romance and love?
Go on.
Swiping left and swiping right,
Love powers everything.
But sure, we can be capitalist about it. Good.
Right. So acquisitions and mergers. What do I mean by that? Well, in the early days, horizontal gene transfer, there was all sorts of back and forth of open source. Life was open source.
Yeah.
You give me your code, I'll give you my code. Right. Unix, Red Hat, et cetera. Right. So horizontal gene transfer dominated in the early days. Then once things really started to be...
But by which we mean, for those who don't know, it's not just that you're a little microbe and you split and you duplicate your genes, and that's the only thing that happens with the occasional mutation, but also literally you take in DNA from your neighbor or give it DNA to your neighbor.
Exactly. So
it's crazy talk, but okay.
You're looking at the biological GitHub and you're
forking and splitting and whatever it is you do. Yeah. Merging.
But then as things got a little more complicated, you start to be more compartmentalized and less porous. And then instead of just grabbing genes, those early microbes started to kind of subsume other microbes. Bacteria gobbled up other archaea, or, back then, who knows what they actually qualified as. Right. But single-celled organisms engulfed other organisms. They acquired their capability, just like, a Google would acquire I don't know what the heck is Google acquiring everything, right?
Yeah, I don't know. Some self-driving car, yeah.
Right. So this acquisitions and mergers strategy is very true in the history of life on Earth.
But when did that happen? When did that...
So there's a lot of debate about the timescales for when do mitochondria, right, an organelle, which once upon a time was an independent microbe, when did that get incorporated? When do the cyanobacteria that really did the business of photosynthesis, when did they get incorporated into other cells? And even the nucleus, right? There's a lot of debate about that. And within the biology community, once upon a time, there were prokaryotes and eukaryotes. No nucleus, and you've got a nucleus. Mm-hmm. But what the tree of life is telling us, and what the study of life on Earth is telling us, is that there's a lot more to it.
It's not that simple, I know. Yeah, it never is that simple. That's why you should do physics instead of biology.
F equals MA.
Exactly, it's all you need.
But so fast forward to the emergence of multicellular life, because I want to get you the squids on Europa.
Yeah, I know.
Thankfully, life on Earth began to utilize the energy from the sun, our parent star, and was able to start converting the CO2 to oxygen. And the initial stage of that pumping of oxygen into our atmosphere caused the ocean to rust out, essentially oxidizing a lot of the iron in our ocean, forming what we now see as banded iron formations, which are where we go to mine iron. And then once the ocean rusted out, we started building up oxygen in our atmosphere. And once oxygen levels got to a sufficient level, a few microbes started to realize that if they teamed up, they could collaboratively utilize the oxygen and some of the organics in solution to do the metabolism that we now know and love and depend upon, which is that heterotrophy of eating organics and burning them with oxygen.
So you're saying that the transition to multicellularity was not just a bunch of random bumping into each other, but it was opportunistic.
Totally opportunistic. Think about it like, if we go back to the battery analogy, a lot of microbes have figured out ways to survive on the tiniest of watch battery. Mm-hmm. Methanogens and sulfate reducers operate with tens of kilojoules per mole of a negative change in Gibbs free energy. Compare that to the hundreds of kilojoules to thousands of kilojoules that are needed by larger organisms such as us. And so, it was an energetically opportunistic innovation to utilize the oxygen in the air as the oxidant and the organics in the environment as the reductant.
So Europa.
So on Europa, this in my dream of dreams.
Yeah. It's late in the podcast. We can dream a little bit. Let's let our hair down here.
Right. So as I mentioned, the radiation processing produces oxygen in the ice, and the ice of Europa is geologically young. The surface of Europa globally is tens of millions of years old. That's a flash of a pan, geologically speaking. That's comparable to the age of our oceanic crust here on Earth, and those are some of the youngest rocks on Earth. So on Europa, if the ice is cycling into the ocean directly, and that's a significant if. We don't know much about the conveyor belt type of motion of the ice and what may or may not be happening. Subduction, subsumption, all sorts of things like that. But if the ice is delivering oxygen to Europa's ocean on a relatively short geological timescale, you could have enough oxygen in Europa's ocean to support organisms on Earth. You could get those concentrations that are found in some of the O2 minima zones in Earth's ocean.
I get it.
And there you find polychaete worms and
So the
shrimp
motivation
and
for multicellular life might be there on
could
Europa.
be there, even without the sun shining.
Yeah. So we should tell the audience you were a consultant on the movie Europa Report.
Correct.
And I'm not going to give away anything except that, yes, they go to Europa and they find life.
Yeah.
Boy, do they find life. Yeah.
Yeah. And if you haven't seen the Europa report, that the writing team, the production team, the actors, et cetera, that was a great project to be a part of. And you and I have worked on various movie consults together and had a lot of fun.
That one was closer to the real science than most of the ones we've done.
So, I think you and I worked on Thor together with Kenneth Branagh, and we can come to that. But for the most part, I don't know what your opinion is, but we can add suggestions and kind of try and guide the vector of where it will go. But at the end of the day, it's no big rub on us if they don't actually take our advice. With the Europa report, my colleague Steve Vance and I this is really close to home. So,
we care a little bit more about what's going on here than we do on Asgard.
Yeah. And so if you're going to do this, can you at least commit to us that you're going to try and get things right? And they did. They were absolutely brilliant.
Yeah, I love the movie. It was a low budget movie that really did a very good job.
For something like $8 million, the zero-G stuff that they did, most large budget films
good movie magic.
Use a vomit comet to get zero-G. The brilliance of that team, they used green yoga balls and had the actors on their backs and on their stomachs rolling on green yoga balls in the little capsule to give the appearance of floating in space. I love that kind of clever way of going about things.
I think that, I hope that there are the squid in Europa. I think that would be very cool. But let's sort of wrap things up with the lessons for beyond the solar system that we might get from the solar system. I mean, one obvious thing is if we found, so let's say that we really do a good job at looking at Europa, Enceladus, Titan, and we either find life on all of them or on none of them. Mm-hmm. How willing will you be to then extrapolate that to lessons for the rest of the universe?
Right. This is a great and very important question. So if we do a robust exploration of the alien oceans beyond Earth, Europa, Enceladus, Titan, Pluto, Triton, you name it, we will either find evidence of life or not. I think both answers are equally profound. So if we find life, then it's kind of off to the races. The origin of life is easy. Life should arise wherever the conditions are right. Europa-type worlds are potentially ubiquitous in our universe, and we could live in a biological universe. Conversely, if we don't find evidence of life on these worlds, that gives us important information on hypotheses for the origin of life.
Yeah.
That would tell me that, the origin of life most likely does not occur around hydrothermal vents, and it does not occur in icy environments. And we didn't talk much about origins in ice, but that's a whole nother thread.
Or it just almost never occurs.
Or it almost never occurs. But in the case of not finding life in these alien oceans beyond Earth, I would say then that the origin of life does require continents and the warm tide pools and the types of...
That would be evidence for that, right?
Yeah. So Europa has no continents. There's no rivers and tide pools. So we can add to the information content even with a null result. Right. And granted, a null result would be hard to come by. You'd have to explore pretty thoroughly, but
you're willing to spend that money.
Well, and the other thing is that Europa's ocean, Enceladus's ocean, these are global oceans, and so if you sample in a few places, the ocean flows around, and you can at least have some confidence in the connectivity. But so then extrapolating to our galaxy and the universe more broadly, if we don't find life in our own backyard, if we don't find it on Mars or within these alien oceans, then I think we start to enter a realm where life on Earth is a biological singularity. It operates in the truest form of singularity, where, our evidence for life on Earth would say that it is a layer on top of biology, and the Gibbs free energy, all these things should, the laws of physics.
On top of chemistry.
On top of chemistry.
Geology, sorry. You said geology, right.
So physics is the base, chemistry and geology are the layer there, and then biology is sort of a fancy
But you're saying
layer.
that we have enough other opportunities to find life in the solar system that if we don't, it really does suggest that maybe it's not that ubiquitous.
That's right. And that continents and Earth-like worlds are required for the origin of life. Now, Mars serves as a good template for that. If we do find evidence of life on Mars, it could be a standard bearer for life existing on another world. But coming back to what we talked about earlier, I would be reluctant to endow it with a second origin just because of the...
That'd be tricky, especially if it were very similar.
Exactly.
Yeah, right.
And so... then we get to this issue of a biological singularity. The laws of physics as we know it, the laws of chemistry, geology, et cetera, lead to chemical disequilibrium, Gibbs free energy kind of being a motivator for the metabolisms of life, and life being kind of a tool that the universe uses to increase entropy and to accelerate us to that entropic death. But if it arises only on Earth, perhaps something else is sparking the fire.
So what is your final question? What is your favorite solution to the Fermi paradox of why we have not seen life elsewhere? We could imagine that life is rare, that multicellular life is rare, that technological life is rare, or that technological life is everywhere and they're just not talking to us. Do you have a favorite one of these?
Right. So I'll answer this in two parts. First and foremost, and I worked at the SETI Institute many years ago, and one of my favorite experiences as a young scientist was approaching Frank Drake after a seminar. And I was a young intern up at NASA Ames at the time. And Dr. Drake,
of the Drake equation fame, yes.
I said, I've long been thinking about all this stuff, and it's an honor to meet you and all that stuff. And I said, well, what do you think would be the next intelligent species on planet Earth if you fast forward the timescales for what's happening on planet Earth? Without missing a beat, he said, squirrels and raccoons.
Really?
Right?
Okay.
And so I thought he was going to say dolphins and whales and all these things. But
chimps or squid?
Right. But squirrels and raccoons, in part because they are living and surviving and developing in such close proximity to the intelligence that currently exists.
So they're being selected for cleverness.
Right. And so I love that answer. But with respect to the Fermi paradox, my primary answer is we just have not done enough searching. I think it's a poorly framed paradox.
Well, Fermi, as I understand it, the original version of the paradox was if you could build self-replicating probes, they could fill the galaxy pretty quickly.
Right.
And we would notice that.
Right. The Turing machines, et cetera. And you could populate the galaxy quickly. Would we see that? That is kind of people kind of tuck that under the rug, right?
Yeah.
So I happen to think that the center of the Milky Way galaxy is like Manhattan. Right? We're 8.5 kiloparsecs out from the galactic bulge. We're in the boondocks. We're like in northern Canada, trying to connect to the internet. And we're saying, why can't we dial up? The Fermi paradox is like, why doesn't the internet exist? Oh, well, it does. You're just not in the right place. You haven't,
All right.
connected long enough. And so I do think that.
So it's there, but we haven't found it yet. That's your favorite.
Well, I think we haven't searched in enough ways and in enough clever ways. And by clever, I mean we've got to cover more of the radio spectrum, but we also need to think about optical SETI. We need to think about ways in which advanced civilizations would communicate with each other.
Right.
So answer A is we haven't searched enough. Answer B comes to that, would we really see them? And one of my favorite answers to this is the dark forest. If you read the three-body problem, that trilogy of books that goes into contact with alien civilizations, et cetera, I highly recommend that trilogy. I want to talk about it, but I don't want to spoil it for people.
Don't spoil it.
Yeah, I won't spoil it. But
it is worth reading. I agree.
Yeah, but basically the point is
St. John Lu.
Correct. You probably have the pronunciation much better than I.
Well, close anyway. Sorry.
But the basic point is like, it's not always advantageous to broadcast your existence.
Right.
And so we kind of take it for granted that, of course, if life's out there, it's going to
want to talk to us.
Right.
Yeah.
So that's my part A and part B answer to the Fermi paradox.
Good. Well, we'll get some data once you get your spacecraft up there, and maybe around 2030 we'll have you back on the podcast to talk about results from your lander.
Potentially sooner than that. For the love of God, we've known each other for a long time. But listen, like, think about it. The year you just mentioned, 2030, 2035, 2040 even. How exciting is that?
Oh, it's very exciting.
Within
this could
the
be
next
the century.
few decades, exactly. Right. So whether it's Dragonfly going to Titan, Clipper going to Europa, hopefully a lander going to Europa, hopefully a mission that'll fly through the plumes of Enceladus, exoplanets going gangbusters, SETI hopefully taking on a broader and broader search and surveying those exoplanets. Within the next few decades, we could potentially answer this primordial, age-old question of, are we alone? Yeah. And that's, going to revolutionize biology. It's going to revolutionize how we think about our place in the universe.
Yeah.
And so for all of the pains and agony of trying to operate on these timescales, we do live in a beautiful time where we might transform the universe in which we live into a biological universe.
Can't think of a better any place than that. Kevin Hand, thanks so much for being on the podcast.
Thanks, Sean. A lot of fun to see you and chat with you.